Good day everyone. In this lesson, I'm gonna show you how to implement a linear regression in Phyton using Google Colab. Actually, Google Colab is a powerful tool to code any kind of programming languages, which you can access freely using your desktop or your mobile phone. I will send a tutorial video later on how to use the Google Colab. And now, it's time to start implementing linear regression in Phyton. Basically, all you should do is apply the proper packages and their functions and classes. The package NumPy is a fundamental Python scientific package that allows many high-performance operations on single and multi-dimensional arrays. It also offers many mathematical routines, and of course, it's open source. The package scikit-learn is a widely used Python library for machine learning built on top of NumPy and some other packages. It provides the means for pre-processing data, reducing dimensionality, implementing regression, classification, clustering, and more. Like NumPy, scikit-learn is also the open source. If you want to implement linear regression and need the functionality beyond the scope of scikit-learn, you should consider stats models. It is a powerful Python package for the estimation of statistical models, performing tests, and more. It's open source as well. Let's start with the simplest case, which is simpler linear regression. Then I will open here the Google Colab. Just type Google Colab on your Google browser. Then I have here the I have here my works here. So actually there are five basic steps when you're implementing linear regression. The first one is to import the packages and classes you need. Number two is to provide data to work with and eventually do appropriate transformations. Number three, create a regression model and fit it with existing data. Number four, check the results of model fitting to know whether the model is satisfactory. And number five, apply the model for predictions. So I will open here my first work here. Okay, so these steps are more or less general for most of the regression approaches and implementations. Step one, here I have here the title which is the simple linear regression with scikit-learn using scikit-learn. Okay, so first one is to import packages and classes. The first step is to import the package numpy here and the class linear regression from sklearn model here. So now you have all the functionalities you need to implement linear regression. The fundamental data type of numpy is the array type called numpy and the array. The class sklearn that linear model, that linear regression will be used to perform a linear and polynomial regression and make predictions accordingly. Step two is to provide data. This second step is to define data in order to work with. The inputs regressors X here and the output which is the predictor Y. So here is the our regressors and here is the predictor. Okay, this should be the arrays. The instances of the class numpy that and the array here are similar objects. This is the simplest way of providing data for regression. So I have here the code. So if I would like to uh, click this button, so first we have to run this first. Okay. We'll wait to create the check here. So it means it's finished. Okay, so here. And next, let's us check here the code. Okay. Then now you have two arrays. the x and y array, or the input x and the output y array. So you should call that reshape here. Why we should have to write the reshape here in x? Because this array is required to be two-dimensional, or to be more precise, to have one column and as many rows as necessary. That's exactly what the argument -1 and 1 of the three shapes specifies here. So let's try to run the x and y by using different method. Okay, by using this code, let's try to run this program. So here is the output. Okay, here. Then let's try to print the y. Yes, this is the result. This is for the x and this is for the y. As you can see, x here has two dimensions, and x that shape is 6 and 1. I mean, 1, 2, 3, 4, 5, 6 rows and 1 column. While y here has a single dimension, and y that shape is equal to 6, 1, 2, 3, 4, 5, 6. So the next step is to create a model and fit it. Okay, so first, this step is to create a linear regression model and fit it using the existing data. So let's create an instance of the class linear regression, which will represent the regression model. So let's type here the model linear regression. Let's try to run this. Okay, so these statements creates the variable model as the instance of linear regression. You can provide several option parameters to linear regression. First is the fit underscore intercept. It is a Boolean. It is true by default that decides whether to calculate the intercept 0, which is true, or consider it equal to 0 or false. Or pwede ding normalize, which is a Boolean, false default, that decides whether to normalize the input variables, or true, or not, it is false. And copy underscore x is a Boolean also, true by default, that decides whether to copy or true or overwrite the input variables or false. And n jobs is an integer or none or default and represents the number of jobs used in the parallel computation. This example uses the default values of all parameters. So it's time to start using the model. First, you need to call the .fit on model here. So model.fit x and y. Let's try to run this. Okay, here is the results. So with the using the .fit, you calculate the optimal values of the weights 0 and 1 using the existing input and output x and y as the arguments. In other words, that fits the model. It returns self, which is the variable model itself. That's why you can replace the last two statements with this one. Model is equal to linear regression that fit x and y. Let's try to run this. So this statement does the same thing as the previous two. Here, 1 and 2. So it's just shorter. So pwedeng to or pwedeng ding ito. Then step 4, get results. Once you have your model fitted, you can get the results to check whether the model works satisfactorily and interpret it. You can obtain the coefficient of determination R squared with that score here on model. So let's try to run this sample. Okay, r underscore squared is equal to model that score x and y, run in the program. And let's use the function print for coefficient of determination. So here is the result coefficient of determination 0.71. Okay, so when you're applying that score here, the arguments are also the predictor x and regressor y. And the return value is r squared. The attributes of model are that intercept here, which represents the coefficient 0, and that coef, which represents 1. So let's try to run this. So this code illustrates how to get 0 and 1, and you can notice that that intercept is a scalar, while the that coef is an array. The value of 0 is equal to 5.63 approximately. Illustrates that your model predicts the response 5.63 when x is 0. And the value for 1 is equal to 0.54. Means that the predicted response rises by 0.54 when x is increased by 1. You should notice that you can provide y as a two-dimensional array as well. In this case, you'll get a similar results. So this is how it might look. New model is equal to linear regression that fit x and y that reshape -1 and 1. Print intercept by using intercept and this look for that intercept and that coef. So let's try to run this. Also this. We will get the result 5.63 for intercept. And here for slope, the 0.54. As you can see, this example is very similar to the previous one, but in this case, that intercept is a one-dimensional array with a single element 0, and that coef here is a two-dimensional array with a single element 1. Okay, so step number 5 is response, predict response. So once there is a satisfactory model, you can use it for predictions with either existing or new data. To obtain the predicted response, we will use the that predict. So y underscore predict model that predict x. Use the function print and predicted response y predict and this code. So let's try to run these two and there. Okay, so we have the predicted response of here's the result. So when applying that predict that you pass the regressor as the argument and get the corresponding predicted response. So this is a nearly identical way to predict the response. But what about for multiplying the each element? So we will use this command. So predict and model.intercept plus model.coef, and using the print function. Let's try to run this. Then this is the predicted response for that coef. So in this case, you you multiply each element of x with model.coef, okay, and add model that intercept to the product. The output here differs from the previous example, only in dimensions. Here, same as here. The predicted response is now a two-dimensional array, while in the previous case it had one dimension. If you reduce the number of dimensions of x to 1, these two approaches will yield the same result. You can do this by replacing x with x dot reshape to -1 or x dot flatten or x dot revel when multiplying it with model.coef. In practice, regression models are often applied for forecast. This means that you can use fitted models to calculate the outputs based on some other new inputs. So let's try to run this code. We will get the result 0 to 4. And for y, so here is the result. So here, the depth predict is applied to the new regressor x new here and yields the response y new. Here is the response. This example conveniently uses a range from numpy to generate an array with the elements from 0 inclusive to 5 exclusive. That is 0, 1, 2, 3, and 4. Linear regression is sometimes not appropriate, especially for nonlinear models of high complexity. Fortunately, there are other regression techniques suitable for the cases where linear regression doesn't work well. Some of them are support vector machines, decision trees, random forest, and neural networks. These are numerous Python libraries for regression using these techniques. Most of them are free and open source, and that's one of the reasons why Python is among the main programming languages for machine learning. The package scikit-learn provides the means for using other regression techniques in a very similar way to what you've seen. It contains the classes for support vector machines, decision trees, random forests, and more. So now you know what linear regression is and how you can implement it with Python and the three open source packages using NumPy, scikit-learn, and stat models. You use NumPy for handling arrays. Linear regression is implemented with the following. First is the scikit-learn. If you don't need detailed results and want to use the approach consistent with other regression techniques, you can use the scikit-learn. But if you need the advanced statistical parameters of a model, you need the stats models. Both approaches are worth learning how to use and exploring further. When performing linear regression in Python, don't forget to follow the steps. First is to import the packages and classes you need. Second is to provide data to work with and eventually do appropriate transformations. Step 3 is to create a regression model and fit it with existing data. Number 4 is to check the results of model fitting to know whether the model is satisfactory. And step number 5 is to apply the model for predictions. So that's all for our linear regression. So thank you.